Welcome to Organic Chemistry in One Shot. Whether you're preparing for your Class 11-12 boards or aiming for JEE, this session is your complete guide. We'll start from the very basics and build up to complex biomolecules, ensuring you grasp every key concept along the way. Expect clear explanations, step-by-step visuals, and plenty of motivation to keep you going. Let's dive in and make organic chemistry simple, logical, and even fun. Ready? Let's begin our journey with the foundation of organic chemistry, the element carbon. At the heart of organic chemistry lies the element carbon. Carbon is unique because of its ability to form 4 covalent bonds, allowing it to create a vast array of compounds. Its small size and high electronegativity make it incredibly versatile. This property is the reason why organic chemistry is so rich and diverse. In this scene, we'll explore the atomic structure of carbon, its position in the periodic table, and why it forms the backbone of organic molecule. Understanding carbon is the first step to mastering organic chemistry. Catenation is the ability of carbon atoms to link with each other, forming long chains and rings. This property is what allows for the incredible variety of organic compounds. Carbon can form single, double, or triple bonds with itself, leading to straight chains, branch chains, and cyclic structures. We'll look at simple diagrams to visualize how catenation works and why it's so important in organic chemistry. This concept sets the stage for understanding hydrocarbons and more complex molecules. Hydrocarbons are the simplest organic compounds, made up of only carbon and hydrogen. They are classified into alkanes, alkenes, and alkynes based on the types of bonds present. Alkanes have single bonds, alkenes have at least one double bond, and alkynes have at least one triple bond. We use clear visuals to show the differences and discuss their general formulas. Understanding hydrocarbons is crucial, as they form the foundation for more complex organic molecules. Let's focus on alkanes, the simplest hydrocarbons. Alkanes follow the general formula CnH2n+2 and are also known as saturated hydrocarbons. They form straight or branch chains and are relatively unreactive due to their strong C and CH bonds. We'll look at examples like methane, ethane, and propane, and discuss their physical properties such as boiling point and solubility. This understanding will help you recognize alkanes in various organic reactions. Alkenes and alkynes are unsaturated hydrocarbons. Alkenes have at least one double bond, general formula CnH2n, while alkynes have at least one triple bond, general formula CnH2n2. These multiple bonds make them more reactive than alkanes. We'll explore their structures, naming conventions, and some common examples like ethene and ethyne. Understanding the differences in bonding helps explain their unique chemical behaviors. Aromatic compounds such as benzene are a special class of organic molecules characterized by ring structures with delocalized electrons. Benzene, with its 6 carbon atoms arranged in a ring, is the most well-known aromatic compound. We'll discuss the concept of resonance and why aromatic compounds are unusually stable. Recognizing aromaticity is key for understanding many reactions in organic chemistry. Functional groups are specific groups of atoms within molecules that determine the chemical properties of those molecules. Common functional groups include alcohols, aldehydes, ketones, carboxylic acids, and amines. We'll introduce each group with clear diagrams and explain how they influence reactivity and naming. Mastering functional groups is essential for predicting reactions and understanding organic chemistry. Naming organic compounds systematically is crucial for clear communication. The IUPAC system provides rules for naming based on the longest carbon chain, functional groups, and substituents. We'll break down the steps, identify the parent chain, number the carbons, name substituents, and assemble the name. With practice, you'll be able to name even complex molecules with confidence. Let's apply the IUPAC rules to real examples. We'll name simple alkanes, alkenes, and compounds with functional groups. For instance, 2-methylpropane and 3-chloropentone. We'll also discuss common mistakes and tips for avoiding them. Seeing the rules in action will help solidify your understanding and prepare you for exam questions. Isomerism is the phenomenon where compounds have the same molecular formula but different structures or arrangements. There are 2 main types, structural isomerism and stereoisomerism. We'll introduce the concept with simple visuals and explain why isomers are important in organic chemistry. Understanding isomerism helps explain the diversity of organic compounds. Structural isomerism occurs when molecules differ in the connectivity of their atoms. Types include chain isomerism, position isomerism, and functional group isomerism. We use diagrams to show how butane and isobutane are chain isomers, and how position isomers differ in the location of a functional group. Recognizing structural isomers is essential for understanding organic reactions and properties. Stereoisomerism arises when molecules have the same connectivity but differ in spatial arrangement. The 2 main types are geometric, cis-strands, isomerism, and optical isomerism. We'll explain each with simple models and show how double bonds or chiral centers lead to different isomers. Understanding stereoisomerism is crucial for topics like biomolecules and drug action. Geometric isomerism, also called cis-strands isomerism, occurs in compounds with restricted rotation, such as alkenes. We use diagrams to show how the arrangement of groups around a double bond leads to different physical and chemical properties. Recognizing cis and trans forms is important for understanding reactivity and biological activity. Optical isomerism arises from chiral centers, carbon atoms bonded to 4 different groups. These isomers are mirror images that cannot be superimposed, called enantiomers. We use models to show how chirality affects properties like optical activity. This concept is especially important in biochemistry and pharmaceuticals, where different enantiomers can have very different effects. Understanding how and why reactions occur is a key part of organic chemistry. Reaction mechanisms explain the step-by-step process by which reactants turn into products. We'll introduce the main types: substitution, addition, and elimination. Knowing the mechanism helps you predict products and understand reaction conditions. In substitution reactions, one atom or group in a molecule is replaced by another. These are common in saturated hydrocarbons like alkanes and aromatic compounds. We'll look at examples such as halogenation of methane and discuss the mechanism step by step. Understanding substitution is essential for many organic synthesis processes. Addition reactions occur when atoms are added to a molecule, typically across double or triple bonds. Alkenes and alkynes undergo addition reactions such as hydrogenation or halogenation. We'll break down the mechanism and use visuals to show how the reactants combine. Addition reactions are important for converting unsaturated compounds to saturated ones. Elimination reactions are the reverse of addition reactions. Here, atoms or groups are removed from a molecule, often resulting in the formation of double or triple bonds. We'll discuss common examples like dehydration of alcohols and dehydrohalogenation. Understanding elimination helps explain how unsaturated compounds are formed from saturated ones. Hydrocarbons undergo a variety of reactions depending on their structure. Alkanes mainly undergo substitution, while alkenes and alkynes favor addition. Aromatic compounds have their own unique reactions, such as electrophilic substitution. We'll summarize the key reactions for each type and provide tips for identifying them in questions. Alcohols are organic compounds containing an OH group. They are classified as primary, secondary, or tertiary based on the carbon to which the OH is attached. We'll discuss their physical properties such as boiling point and solubility and their chemical reactions, including oxidation and dehydration. Recognizing alcohols and their reactions is important for both boards and JEE. Aldehydes and ketones are carbonyl compounds containing a C=O group. Aldehydes have the carbonyl at the end of the chain while ketones have it in the middle. We'll compare their structures, physical properties, and key reactions like nucleophilic addition. Understanding these differences is crucial for identifying and predicting organic reactions. Carboxylic acids contain the COOH functional group and are known for their acidic properties. We'll discuss their structure, naming, and key reactions such as esterification and decarboxylation. Carboxylic acids are found in many biological molecules and are important in both synthetic and natural chemistry. Amines are derivatives of ammonia, containing one or more alkyl or aryl groups attached to nitrogen. Amino acids, the building blocks of proteins, contain both amine and carboxylic acid groups. We'll explore their structures, classification, and importance in biology. Understanding amines and amino acids is essential for biomolecule chemistry. Ethers have an oxygen atom linking two alkyl or aryl groups, while esters are formed from acids and alcohols. We'll discuss their structures, naming, and key reactions. Esters are known for their pleasant fragrances and are widely used in industry. Understanding ethers and esters helps in recognizing functional group transformations. Halogen derivatives are organic compounds where one or more hydrogen atoms are replaced by halogens F, Cl, Br, I. We'll discuss their classification, physical properties, and reactions such as nucleophilic substitution and elimination. These compounds are important intermediates in organic synthesis and pharmaceuticals. Aromatic compounds like benzene undergo substitution reactions rather than addition. We'll explain electrophilic aromatic substitution using examples like nitration and halogenation. Understanding the mechanism and directing effects is crucial for predicting products in aromatic chemistry. Polymerization is the process by which small molecules, called monomers, join to form large chains or networks known as polymers. We'll discuss addition and condensation polymerization, with examples like polyethylene and nylon. Understanding polymerization is important for both synthetic materials and biological macromolecules. Biomolecules are organic molecules essential for life, including carbohydrates, proteins, lipids, vitamins, and nucleic acids. We'll introduce each class and explain their biological roles. Understanding biomolecules connects organic chemistry to biology and medicine, making the subject more relevant and interesting. Carbohydrates are energy-rich biomolecules made of carbon, hydrogen, and oxygen. They are classified as monosaccharides, disaccharides, and polysaccharides. We'll discuss their structures, functions in the body, and examples like glucose and starch. Understanding carbohydrates is key for both biology and chemistry exams. Proteins are polymers of amino acids and perform a wide range of functions in living organisms. We'll discuss their structure from primary to quaternary levels and their roles as enzymes, hormones, and structural components. Understanding protein structure and function is crucial for both organic chemistry and biology. Lipids are a diverse group of biomolecules including fats, oils, and phospholipids. They are important for energy storage, cell membrane structure, and signaling. We'll discuss their structure, classification, and biological functions. Understanding lipids helps explain many physiological processes and health topics. Vitamins are organic compounds required in small amounts for normal metabolism. We'll classify them as water-soluble and fat-soluble and discuss their sources and functions. Understanding vitamins is important for both health and exam preparation, as questions often focus on their roles and deficiencies. Nucleic acids, including DNA and RNA, store and transmit genetic information. We'll discuss their structure, components, nucleotides, and functions in protein synthesis. Understanding nucleic acids bridges chemistry and biology, making this topic vital for both boards and competitive exams. Enzymes are proteins that speed up biochemical reactions. We'll discuss how enzymes work, their specificity, and the concept of activation energy. Understanding enzymes is crucial for topics in both organic chemistry and biology, especially when studying metabolism and reaction mechanisms. Hormones are organic molecules that regulate physiological processes. We'll discuss their types such as steroid and peptide hormones and their roles in the body. Understanding hormones connects organic chemistry to real-life biological functions, making the subject more meaningful. We'll look at common vitamins and the diseases caused by their deficiencies, such as scurvy, vitamin C, and rickets, vitamin D. Understanding these relationships helps in both exams and real-life health. We'll also discuss sources of vitamins and tips for remembering them. Let's quickly recap the major topics we've covered: the basics of carbon and catenation, types of hydrocarbons, functional groups, IUPAC nomenclature, isomerism, reaction mechanisms, and biomolecules. This summary will help you organize your revision and focus on the most important points for your exams. Here are some quick revision tips. Make summary notes for each topic, practice drawing structures, and solve as many problems as you can. Focus on understanding concepts rather than rote memorization. Use flashcards for functional groups and reaction mechanisms. Regular revision and practice are the keys to mastering organic chemistry. For board exams, focus on clarity and stepwise answers. For JEE, practice MCQs and time management. Understand the pattern of questions and revise previous year's papers. Stay calm and confident during the exam. Remember, understanding the basics will help you tackle even the toughest questions. Students often make mistakes like confusing isomers, misnaming compounds, or forgetting reaction conditions. Always double-check your answers, especially for IUPAC names and mechanisms. Practice regularly to avoid these common pitfalls and build your confidence. Organic chemistry can seem challenging, but with consistent effort and the right approach, you can master it. Remember, every expert was once a beginner. Stay curious, keep practicing, and believe in yourself. Success in boards and JEE is within your reach. Good luck and keep learning. Thank you for joining this comprehensive session on organic chemistry. Review your notes, revisit tough topics, and keep practicing problems. Stay tuned for more educational content to help you excel in your studies. Wishing you all the best for your exams and beyond. For further study, use NCERT textbooks, reference books like Morrison and Boyd, and online resources for practice questions and video explanations. Join study groups and discuss doubts with peers. The more you engage with the material, the stronger your understanding will become. Remember, organic chemistry is a journey. Every concept you master brings you closer to your goals. Stay positive, keep revising, and never hesitate to ask for help when needed. You have the potential to achieve great things. Believe in yourself and keep moving forward.